Our next speaker is Tommaso Demarie. So Tommaso did his PhD in Australia in Macquarie University, where he looked at quantum information and in particular relativistic quantum information. Since then, he was a research fellow at the Center for Quantum Technologies and SUTD. And after that, he looked at academia and industry and decided that industry was a more exciting path to take. And also in 2018, founded the company Entropica Laboratories. So Entropica is focused on sort of the applications of quantum information and quantum technologies. And this is a topic that Tommaso will share with us about his vision for what quantum computers can do and what they mean for the industry. Thank you very much.
What I want to tell you about is, first of all, who I am, who we are at Entropica, but also I would like to give you a few insights on the challenges and also the exciting bits of attempting to build a quantum computing company, what it means for, especially for a person like me who has a very heavy academic background, who prior to the company has always, well, not always, but most of my time worked at a university. And the reality is that it can be quite a radical shift to go from being a researcher to being, a manager, CEO, whatever. These are just titles, right? But when you try to build something ideally big and long-lasting, it can be incredibly challenging, especially when you're not trained to think that way. So this is a little bit of an agenda for today, introduction, all of that, but also I want to speak about OpenQA, which is a product where we have released a couple of months ago. I hope it will be interesting for you. It could lead to potential collaborations or something that you might be working on as well if you are interested. I don't know how many people in the audience have a quantum computing background or quantum physics background. I don't know how many of you are actually working on quantum computing today or want to work on quantum computing, but I hope to be able to give you a few ideas on what you could do and also what you could do with us at Entropica, since the last question was about internships and potential collaborations, right? Okay, so let's start. I mean, Joe has done an amazing job, right? He has very well explained the challenges with quantum computing today. So some of the things I might say will be redundant, but it's okay. Like, it's always important to hear important concept more than once. So why does quantum computing matter? Well, quantum computing matters because of this concept of quantum speedups. So at least theoretically, there have been a few demonstrations, but let's say theoretically with a quantum computer, you can solve certain problems up to exponentially faster than you could with any supercomputer, any conventional classical computer. As far as we know, to do that for useful problems, when I say useful, it's a bit of a weird word because it doesn't have any objective meaning per se, but what I mean here are solving, basically what I mean is being able to solve problems that have a value for humans, for us. And as far as we know, to be able to do that, you actually need a large number of qubits. We don't know exactly how many. That will depend on the quality of the qubits and the quality of the control that we have moving forward. But let's say hundreds of thousands, potentially millions of physical qubits on a machine. So today, nobody has that. If you remember what Joe was saying, the largest device available today where you can individually control qubits has a few hundreds. It's likely that we're going to have a few thousands next year or maybe in the next 2 years, but still far from the target here. And even having a large number of qubits won't be enough. You need to be able to control them, but you also need to be able to suppress errors that accumulate in a quantum computation. So quantum systems are very fragile. When you try to run a quantum computation, nature, which means everything else, that is not the quantum computer, and actually the quantum computer itself, because qubits can interact with each other, will cause a disturbance in the system. You need to be able to suppress that so that the computation can run as intended. To do that, there's been a lot of work on a concept known as quantum error correction. I won't be speaking about quantum error correction today, but the reason why I'm bringing it up is because I think it's very important for people to be aware that moving forward is not only about having many qubits, but it's also about using the qubits in a meaningful way. All the way to fault-tolerance quantum computing. Fault-tolerant quantum computer is a device that can do what is intended to do, let's say in a noiseless fashion, at least at the logical level. If you have all of that, you can solve hard computations, or at least some hard computations faster than you could with a classical computer. And that's where we want to get. Well, so one thing about Entropica is that the team loves memes to an extreme level. So I have sprinkled a few here and there during the talk. I think what happened is that we have a refresh this presentation. I had removed it, but since it's still there for you to enjoy. We want to get to being able to run Shor's algorithm on a machine to really claim that we made it to full tolerance quantum computing, but we are not there yet. Okay, so where are we today in terms of quantum computing and quantum computing capabilities? You have heard of this word NISQ, near-term intermediate scale quantum computing, noisy intermediate scale quantum computing. These are the machines, or these are the techniques that we have today in the industry. And of course, fault tolerance is the big goal. So what is the difference between the two? You can think of them as the lower bound and the upper bound of quantum computing. There is a lot in between that doesn't really have a name yet. They will still have to meet, to reach. But basically NISQ, let's see if I also laser, yes, we can't see it, so it doesn't matter. So NISQ means we don't know exactly how many physical qubits, but let's say not too many physical qubits, 10, 100, maybe 1,000. Means that there's no active quantum error correction, there's no quantum error correction, you might have error mitigation, but that's it. Computations are limited in runtime because of errors, so you cannot run the quantum computation for too long, etc., etc. The point here is that, as far as we know, there's no guarantee of quantum advantage, there's no guarantee of useful speedups with NISQ machines. Some people might believe that we will have it, the jury is still open on that, but today there's no evidence of that. It's very important to say that now. On the other hand, there is evidence for fault-tolerant quantum computing. As I said, we need a very large number of qubits. We need to be able to run arbitrarily long quantum computations before we can do that. And what we are doing at Entropica is to work on software. So we're also a software company like Horizon is. We're not building quantum computers, we're using quantum computers. And the idea is to be able to design, analyze, and run large-scale quantum algorithms. Of course, in a single sentence, there is a lot of assumptions and ideas buried beneath. So I will proceed by giving you a few insights on what that means in practice. But before doing that, let me say a few words about myself and how this whole endeavor started. So my name is Tommaso, I'm the CEO. I'm one of the two co-founders of the company. The other one is Yuan Muro, who did a PhD at the CQT at the Center for Quantum Technologies at NUS. So I was a postdoc actually with Joe. He was my PI at my time at SUTD. So my background is also in quantum information theory. And just a few dates for you if you want to know how we got here. So prior to 2018, I put CQT simply because it's like an overlap between my experience and Yuan's experience. Is a way to say that we were both working, both studying in academia. And after that, we joined an incubator, Entrepreneur First. It was an interesting experience. Basically, what it's a little bit like military training, I guess. You go there, you spend some time, they try to instill in you some ideas, some concepts that should be useful for what you do next when the event, something happens. And then after 6 months, they kick you out in the open world, and you kind of try to figure it out. So they were our very first investor. It was an incredibly interesting experience. If you have any question about that, I'm happy to say more. But fast forward a couple of years, in 2020 we raised money. So there was a very first big business, if you like, or operational milestone for us. So we raised money from private investors and also from the Singapore government through SGinnovate. I'll just say that Joe has done a very similar thing. SGinnovate is one of the investors of Horizon Quantum as well. Okay, something very, I would say, special about Entropica Labs is that we take a very bottom-up approach, right? So we start with the machines. We love using quantum computers. We have done a lot of that. In fact, we have run hundreds of QQ hours using quite a variety of devices. These are the ones that I can actually publicly speak about, but we have used more that are not there. But that happens behind the scenes, so we have to be a bit careful about mentioning names. And as you can see, is both superconducting quantum computers with IBM Rigetti, but also trapped ion devices with IonQ, and what at the time was called Honeywell, today is called Continuum, or at least that team joined Cambridge Quantum and became a new entity called Continuum, but the device is the same. There's an updated version of the Honeywell machine. So we spent a lot of time working on quantum computers. That is incredibly useful because, well, not only is fun and exciting, but it also helps you to understand how the field is progressing. Now, one is to be very careful with timelines. So there is a timeline on that slide. There is also maybe somewhere near the years, because we don't know, nobody knows, right? But it's okay, you can make reasonable claims looking at how things have been progressing so far. And today we are in the NISQ era, and when I say we want to learn how to design and analyze large-scale quantum algorithms, well, if you take a bottom-up approach, you start with what we have. And today we have NISQ devices, so let's start with that. The question is, how can we design, how can we experiment with large-scale NISQ algorithms? And of course, here at the moment, large-scale is bounded by the size of the machines that are actually available to us. So they're not that large. They're still reasonably big in the, in the grand scheme of things. The next step for us would be moving towards polymer operation calls all the way to fault-tolerant quantum algorithms. I repeat it again, just to make sure that is clear. We don't know when that is going to happen, but we try to think in terms of reasonable timelines, and that seems to us as reasonable as it gets. So you'll see OpenQA on top of the blue box. What is OpenQA? Well, OpenQA is a SDK. So it's a software development kit. It is written in Python, and as Joe was saying, Python is really the high-level interface that we use, in this case, to communicate with the quantum computer. Of course, there's a bunch of steps that happen in between you coding on Python on the laptop and the quantum computer doing something as a consequence of your instructions. But at this point, we're still thinking in terms of easy enough interfaces at the human level. So a lot of our inspiration actually follows from Keras. I guess most of you, maybe all of you, or at least some of you here are familiar with that. So there's also an interface in that sense, and it allows you to very quickly experiment with neural networks for machine learning tasks. So OpenQA does something similar. It allows you to very quickly experiment with, in this case, with QoA algorithms. In fact, there's a bit more than just QoA, but for today's talk it's fine to just think in terms of QoA. I will say a few words about the algorithm in a second. And as far as you can tell, you will be able to design, analyze, and run NISQ, this case QoA algorithms with thousands of qubits. We haven't tested that on a real device just yet, but we have had good success with 80 qubits, so on the order of 100 physical qubits. A few words about OpenQA. If you're interested, it's a bit small. I mean, you can Google it, you will find it. It's actually an open source library, so it's available on GitHub, and the GitHub link is down there. We have an archive paper that came out in October. It's basically a white paper that describes what you can do with OpenQA and how to use it. We are collaborating with the Unitary Fund, which is a large no-profit organization that promotes open source software for quantum computing. They're doing amazing work, and we have a monthly community call organized together with them, where we speak about OpenQA and how the community is growing. So we have a strong community effort in that sense. I really want people to start thinking about quantum computing and using quantum computing in a meaningful way. About 1,500 downloads. It keeps growing, but it's about the order of magnitude at the moment. People are already using it, which is great. So there's a quantum information group at NTU in Germany that is actively using OpenQA. They've already contributed to the code, so they're listed as contributors on GitHub. There was a paper that came out like Monday or Tuesday, by the folks at Jülich, the supercomputing center in Germany also, who basically the authors have used OpenQA for the calculations, so it's great. And we use it extensively for a project with Rigetti. You can read more about that on our blog, on our or a Medium page, and also for customer engagements. So overall, it's very exciting. And QoA, if you don't know what that is the quantum approximate optimization algorithm. It's a nice technique. It's a bit more subtle than that, but let's say it's a nice technique because you can actually run it on today's quantum computer. It splits the work between classical and quantum. So it does most of the work on a classical device and a little bit of the work on a quantum computer, so you basically maximize what you can use or what you can extract from a quantum computer in terms of compute power. Works as a loop. So you have a parameterized quantum circuit. You have some classical parameters. You start, you run, you extract some information from the QPU, from the quantum processing unit. You pass that information to a classical optimizer. Classical optimizer derives new parameters, and the loop continues until you minimize a cost function. This is really the idea. And then you might wonder why QoA. There's not a lot. Joe said there's about 200, or order of 200 quantum algorithms today. There's a few niche techniques that look like QoA in spirit, that is a structure similar, but we focus on QoA because, imagine that tomorrow you can run quantum computations on a 500 qubit QPU and you have like 10 minutes to decide what to do with that. What would you do? Well, it seems to us a reasonable answer to say run QoA. Because QoA is actually quite intuitive. It's a very simple technique per se. It's really neat. It's very beautiful. It can run on today's quantum computers. You can use it to solve optimization problems. And bear in mind, I'm not making any claim whether it's going to be better than classical techniques. But even at today's scale, you can take a simple instance of an optimization, of a combinatorial optimization problem, and code it as a QoA, run it, get a result. So it can do something that tells you what the quantum computer is doing. And in that sense, it's actually quite, quote unquote, useful. It's not maybe valuable, but it's useful. And there's also a great sandbox for NIST devices in that sense. At the same time, you cannot just take it. So there's a paper from 2014, the original paper that introduced QoA. You cannot just take that, implement it, and expect it to run. There's actually a lot of knobs that you need to turn, you need to play with for QoA to do something meaningful, given a specific problem statement. And this is where it gets very interesting, because with OpenQA, you can change all of that quite easily. So it gives you the ability to customize your algorithm and very quickly test it, given a certain problem statement. So that's quite interesting for us, because you can experiment very quickly. In that sense, it, if you like, is inspired by the idea of Keras, which is you want to experiment as fast as you can, given a problem statement and neural networks. And a few more points, but let me just stop here. And this is how it looks like when you think about the whole structure of OpenQA at the design level. Don't worry too much about all the names, but it's just to say that at the preparation phase, when you want to assemble your quantum algorithm, there's a lot of choices that you can make. And usually you would have to corrupt these choices either using, for example, Qiskit or Penny-Lane or whatnot. But here with OpenQA, what we want to do for ourselves and for the users is to give the ability to very quickly just speak what they need. One line of code, and then in the background, you get the description of the quantum circuit, and you can run it on a quantum computer. At the moment, we integrate with AWS Bracket, those little colorful boxes that you see, AWS Bracket, Azure Quantum, which is Microsoft's framework for quantum computing, IBM, and Rigetti. And we're working on a few additional integrations that are not publicly available just yet. So using a single framework, you can actually access a range of quantum computers without having to rewrite your code. Now I take another mean break. Right? So I breathe a little bit. But I'm using this occasion to say again, even if I've already said it, that honestly speaking, we don't expect QoA to give any advantage, any meaningful speed up anytime soon, maybe never. So that is not the point of what we're doing. The point here is we have quantum computers available. We can actually use them. So not only is it great to be able to experiment with it, but we want to be able to understand what you can and cannot do with the devices. It also has a research value, so people are doing a lot of research with QA today. We don't know, as I said, whether it's going to have commercial value or not, but let me just say that at the moment, the near-term uses of quantum computers are certainly not valuable, or they're not going to solve any big problem that we have in the next few years, and that is completely fine. I mean, it's okay. It is important to say it out loud. All right. So now I switch gear a little bit. I mentioned that I would tell you a few things about what it means to do what we're doing, and what it means to work at Entropica. So here are a few faces, right? This is not the full team at the moment. We're actually 13 with a few interns, so it's actually quite an exciting environment for all of us. But the reason why I'm showing that is because it looks like a very diverse team. People have amazing skills. Some have a PhD, some don't. But if you look, if you scratch the surface a little bit, you can bid farewell to your diversity, because the reality is that we're all physicists. Maybe surprising, maybe not. But the reason why I'm bringing this up is because we are still a software company. And this is the struggle with me, right? It's not a scientific question per se. You might want to write a PhD on that. The big question is, how do you turn a group of physicists into a software company? Physicists tend to be a little bit arrogant. Not many of you are physicists today. But one of the words I hear the most when interacting with physicists is actually, well, a sentence is, well, that's bullshit. Refer to any claim you may or may not make. So they can be a bit stubborn. And if you want to build a company, if you want to build a successful company, you need to pass through that mindset, right? When you speak about code has to be reproducible, right? But is more than just that. Especially at the beginning, when we started Entropica in 2018, what would happen is that people would work on the same problem. They would have 3, 4, 5 different code or different implementations of the same thing, which is a nightmare. This is not how you should work, obviously. But at the beginning, I guess we didn't know any better, or you just get too excited. Then it becomes very hard to compare results. It slows you down. It's hard to reproduce. And if you want to supervise, junior team, if you want to work with interns, Joe was pointing out earlier how important it is for students to have supervision, to have meaningful supervision. You cannot just work that way. And at times it felt like, this is a nice analogy, like a circus of cats. Cats are highly intelligent creatures. They can also tend to be a bit independent when they operate, when they do their things. So sometimes with your O10 physicist team, it does feel a little bit like a circus of cats, and you don't want that. So let me elaborate a bit further on that. What do we mean by a new type of quantum research? We spent a lot of time internally, successfully, I claim, to really ingrain this idea that if you want to work on quantum computing in a company like Entropica, you need to update your mindset. So the formal training is the following, right? Everything is a sphere in vacuum. Quantum computers work, quantum algorithms work, everything works. The last experiment you did was during your second year undergrad. Analytical solutions, again, there's a formula somewhere that does what you want it to do, and when you speak about coding, it usually means really shitty MATLAB code without annotations, without comments, that if you look at it 6 months later, you have no idea who wrote it, even if you wrote it. And also very little software experience. And when I speak about software experience, I don't mean, I have installed Anaconda and now I can write something in Python. I mean software experience at the professional level. Now I'm oversimplifying, of course, a complex transition, but let me just say that the new requirements are grounded on the reality, and the reality is that when you use a quantum computer, there are errors anywhere and nothing works, as it should. Joyce really eloquently demonstrated that earlier with a lot of graphs. So that is even just at the quantum computing level, but it gets a bit more subtle, like you need to work with QPUs a lot. And to do that, you need to do it in a very professional way. Professional way means dealing with a lot of mundane tasks, like annotating your data very well, learning how to use databases in a professional way, learning how to use the cloud, make sure that you work, well, whatever way you want to work, you follow it. For example, if you want to work on the cloud, you make sure that your data is not stored locally, you follow good software development, and you follow good overall, let me just say, development practices. Coding is also more than just MATLAB. That just goes without saying, but most importantly, software means a lot of things that usually as a physicist you're not familiar with. API, Dockerization, dashboards, etc., 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 code reviews and all of that. So it was actually really, beautiful to go through all of that. I'm not doing technical work anymore, right? So maybe I observe this transition from the edges, if you like. But it's incredible how much more productive you are, of course, but also it's incredible how the mindset changes in the company when you start to think this way, and when you start to implement this kind of, well, guidelines. Something that was incredibly useful for us was when we hired an experienced system engineer who came in quite brutally and changed a few things that we were doing poorly, and that's been fantastic. It's really beautiful to see. So if any of you is thinking about moving forward, working in a company like Entropica, or even just transitioning from academia to a software engineering or to any startup kind of work, start to appreciate that there is a very valuable transition process waiting for you. Okay, so how does that connect to OpenQA? Well, everything I told you before about OpenQA is really is a value proposition for the users, right? It can do all these amazing things for you, but for us, it was also incredibly important because once you write down some guiding principles that you want to follow, it's be open source, hardware-driven, modular, easy to use, etc., then you can build software that not only is useful for people outside, but is also useful for you, for us. So OpenQA has been really critical to speed up the work in the company, and I think if you're familiar with the work of Paul Graham, who's a computer scientist who started Y Combinator in California, something he says a lot is if you know, one of the principles of starting a startup, if you can, is identify a problem that you have and start with that. Of course, it has to be a big problem, right? If you're the only one experiencing it on the planet, it's hard to become a big company. But under reasonable assumptions, if you can identify problems that you have and that if you can solve, will make your life easier, then you're on a good path. And OpenQA certainly solves a lot of our problems. So let me show you a little bit how it actually looks like if you want to use it. So the beauty of OpenQA is that it gives you a way to literally in 3 lines of code, once you have defined the problem statement, to use a quantum computer, to run QA on a quantum computer and get a solution to a combinatorial optimization problem. So we have a number of classes. In this case, it's a number partition class. This is very simple, of course, but basically what you do here, you call the dependencies, you initiate an instance of the class. So number partition, what it is a list of numbers, and you want to partition them into 2 lists, such that the sum of the numbers in both lists is either equal or as close to equal as possible, given the instance that you have. It is an optimization problem, it's a prototypical optimization problem. So here all we are doing is really instantiate the problem, create an object, a QA object, compile it, and run it. That's it. 3 lines of code, as easy as it gets. The nice thing is that the interface is device agnostic. Device agnostic not for all devices, for the devices I've mentioned earlier. And it compiles the instruction into the actual algorithm without you having to worry about what that is. This may be or may not be what you want to do, it depends. But it really encapsulates the idea of quickly experimenting with a quantum computer today. Of course, you can pass more instructions, and then that changes the way you, well, it changes the technique. You can pick different QA routines and so forth. But the idea is that you can easily and quickly run a QA algorithm on a quantum computer today. You get results, and there's actually a lot of tools for post-processing and for visualization of the information that you get back from a quantum computer, which is really useful, especially if you're doing research in this field. So something else I would like to share with you, something that we have done before I conclude. This goes back to the whole idea of what it means to actually write software today. Not specifically quantum computing software, but just thinking more in terms of software development and software development practices. So something we have been doing, let me just put everything on the slide, something we've been doing in the last months is to integrate OpenQA with Amazon bracket jobs. So what is that? Is basically a way okay, so Amazon or AWS has this platform, this interface called Bracket, which is their product to access and use quantum computers through Amazon Web Services. We spent quite some time to integrate OpenQA with that, so that you can basically package all the instructions, but it's similar to what Joe was describing earlier, by the way. Like, you have a JSON file with the specifics of your QA algorithm, and then you have all the elements that you need to package all of that into a container that is sent to AWS. And what is quite nice about this system is that if you are using AWS, or if you want to use AWS, you can use OpenQA to create QA algorithms directly. And what it does is to package all the information that you need, most importantly, the information that you need to run the classical quantum loop that I've shown you before. And then you pass all of that to AWS, you can close your laptop, forget about it. Once it's done, you can access it on your AWS console. So we love doing that because it starts to becoming a bit more real in the sense of, big question is, how are people going to use quantum computers in 6 months, 2 years, 5 years, 10 years? Well, let's not get too far away in time, but there's a lot of developers who work on AWS, so making sure that they can continue using AWS, they can continue using the cloud as they're used to, but using our tools for us is incredibly important. So it is a very first small step towards making that vision real. Okay, so actually that takes me to the end of what I wanted to share with you. So what comes next? For us, a few things. So we want to continue, of course, building quantum software on real devices. There's 3 aspects we are working on for your own interest. Compilation, errors, error mitigation, and continue improving software practices and making use of all the tools that are available in software development and software deployment today. But the value proposition for you, if you think this is interesting and any of you is actually working on quantum computing today, or any of you is doing any research on these techniques, well, the reality is that we built OpenQA for you. It's useful for us, of course, but at the end, it's a tool for users. So, 3 ideas, right? If you're working on quantum optimization and you find that coding and accessing quantum computers is a frustrating experience, well, then you might want to consider OpenQA, because it might make your life simpler and more fulfilling, and you might be able to write more papers faster. But the other point is that this is an open source project, and we welcome, in fact, we encourage you to contribute to that. It is very hard to do, well, the reality is that people have a lot of amazing ideas, and we don't claim to have all the best ideas. So when people come in and they say, hey, what about this, or how about that? How can we add these features to OpenQA? And the great answer that we have is, why don't you do it? And then commit to it. And you can be listed as a contributor, just like any open source project. So if this is interesting to you, consider that. Because actually, this would be great. We have a Discord channel. I maybe should have put the link for the Discord channel, but you can just contact me and or you can actually find it on the GitHub page. So you can join our Discord. We're very active on that space and seems to be working quite well. There's a researcher from IBM who keeps, the guy is amazing, he keeps posting videos. Every time we add new features to OpenQA, he basically makes a new video, puts it on YouTube with a lot of suggestions, or implement the suggestions, he does another video. And now he has done an amazing work. He showed how in a few hours he could add all the error mitigation features that Qiskit has and integrate it with OpenQA, and it was working really nicely. So we're like, hey, that's great. Why don't you contribute that code? And he's doing that at the moment. The last point is, of course, building beyond QA. So, as I said before, we don't expect QA to be the holy grail of quantum computing by any means. But we very much like the structure of OpenQA as a whole. So something we are exploring now is, first of all, how do you add new features? So hardware companies are adding new features as we speak, and we want to continue adding these features to the base package. But also, something we want to do is to demonstrate that with the structure of OpenQA, you can remove the QA part and have open whatever it is that you're interested in. Of course, now we're speaking about NIST techniques, so this is not going, again, to last forever. But if you have other ideas that you want to explore, we're very happy to hear that, and if possible, to work together. Okay, so thank you very much. I stop here, and if you have any questions, that's good. Thanks.
Yeah, we have about 5 minutes for some questions. The audience. So if you have any questions, please ask away.
Okay, so it's actually not so much of a physics question, but so you mentioned this QA package, it's open source, right? I'm just wondering how you guys make profit.
Okay, sure. You know, the first rule of quantum computing is you never ask about profit. But sure. So the profitability answer lies beyond OpenQA. Let me move so I can see you. So it lies beyond OpenQA. I personally strongly believe in the idea of a community, in this case of a community of developers, right? And I love open source software. I think the whole open source industry for software has been really incredible, right? And contributed a lot to having a world where there's actually a very large number of people who use computers in meaningful ways. So this is our little attempt to contributing to that. Now, whether we plan to make money with OpenQA or not, we have a few ideas on how we can monetize, but let me just answer your question at the moment. So at the moment with OpenQA as it stands, as an open source library, that is not how we plan to make money. That is how we plan to build a community of users around our tools. But this is the first step towards that objective. So I've given you a non-answer to your question. I hope that satisfies you.
No, I support the cause, but is it like meant to be like subsidized as a non-profit?
Oh, I see. Okay, sure. Well, I mean, now you're entering into the whole nitty-gritty details of how a startup grows. So the work that we have done so far, basically you can think of the work that we're doing internally as, well, there's two aspects to it. First of all, the money and everything that we have been doing is a consequence of private venture capitalist investments, right? So they invest into the company and they believe that the company can be profitable and be valuable at some point later in time. So it's the first step. Now what we are doing internally has two parallel routes with a lot of overlap. So something is what you see, like an open source library like OpenQA, and something you don't see. The don't see part is the one that eventually will lead us to monetization. So now when it comes to OpenQA, we'll see how it grows and how successful it is. If it continues to grow, we are happy to spend internal resources to ensure that the project continues to be valuable for users. Are there ways to monetize it? yes, even if it's an open source package, and all the work that we are doing, for example, with AWS, is opening such channel. Yeah. So I'm just giving you a few ideas, or at least a few glimpses of what we're thinking internally.
Yep.
So with the QA at this moment, you say you can run the system with like 1,000 qubit, but the hardware is not ready. So how you verify, how you know that it will gonna work?
That's a good question. So the way you verify it is you want to verify on the largest hardware that is available to you at each point in time. Right? That's really the lazy answer to what you're asking. And then, then you continue to improving your software base with the developments of the hardware. At the essence, this is really what you want to do.
So at the beginning, you say for this approach, right, we have no proven whether it's better than classical computer. So you're still going in that way. So you are hoping that it will be better.
No. So no, okay, that's a nice question actually. We are not hoping that it will be better. In fact, I can tell you we don't think it will. So QA specifically, I mean, if you were to force me to give you an answer on whether it will be better than classical computers or not, I would say not in the short term, and in the long term, it will simply not be relevant anymore, meaning that there are fault-tolerant algorithms that we know are better. And I'm not even talking about optimization in general, right? At some point, you reach a point where you can solve hard problems with quantum computers, and that's where you want to get. The beautiful thing about OpenQA is that it really is a sandbox. It's a way to use in a meaningful way quantum computers today. And for us, as a software development company, it has been incredibly instructive because you learn what you need to do in order to build software that integrates and that let me just say in a bit of an awkward way, that uses quantum computers meaningfully. So you can think of it as a toy if you really like. And that toy teaches you, maybe not everything, but it teaches you a lot about what you need to learn to be able to use quantum computers. And if you can continue using it as the hardware progresses, and you can run QA and 100 qubits, 200, 500, 1,000, then it seems to us that you're on the right path. That's the principle there.
Thank you.
I may wrap up with a similar question from our students, which I guess you already went through a little bit. But in terms of the particular skill sets that you're interested in hiring and current intention opportunities.
Yeah, that's always a good question, right? So I will try not to repeat what Joe answered to that. I think Joe gave a really good answer there. So I'll start with the conclusion of his answer, which was, it's not only about quantum computing. Especially as the company grows, there are skills that most physicists don't have, and they don't have to have, that become very, very important, from project management, product management, design, marketing, anything you can think of. So there are opportunities for people who really have a diverse set of skills. But I mean, I would assume that most of you here have technical background, or mostly have a technical background. So certainly, as cliche as it sounds, being able to code well, I can argue on what that means. Being able to code well is becoming incredibly important, because it allows you to very quickly experiment whatever you're doing, but it also makes it easier to speak internally. Like working only at a mathematical level, it has its value, but it seems to me that it's becoming more and more fundamental, I would say, to be able to code, and also being willing to learn modern software architecture and modern systems architecture. without being an expert, but being comfortable with that, even just, for example, being able to use Git, which might not be a very high bar, but still, most people who approach us for internships usually are not familiar with Git. So we can just start with that. Sorry if I'm rambling a little bit, but what I'm trying to say is that it's not only about the quantum computing part, of course that is important, critical, but it's also about everything that surrounds it and how you bring that idea of quantum computing to the real world.
Great, thank you very much.
Thank you.
Okay.
Thanks everyone.